Well, good morning. I wanted to start today by sharing the material for the lab this week. I still haven't posted the Word document for it, but just wanted to just sort of show you what measurements I took for it. We're determining resistivity, which is, I mentioned yesterday, this microscopic property of materials. And actually, first thing I wanted to do was give you a little bit of more information on that. Let me hit escape and get out of here. The resistance of a material is this property that you can measure directly. And you last week did some resistors, and let's see, I guess the symbol for an ohm meter might just be a circle with the letter ohm in the center of it, but you were able to do it that way. Now, if you were measuring the resistance of just a piece of wire, we would just have a symbol that looked like that, and you'd be doing something like this. Now, turns out what the resistance of that piece of wire depends on is, if you calculate the resistance of it, it's going to be proportional to the length of it. And so the longer the wire, the greater the resistance is going to be. And it's going to be inversely proportional to the cross-sectional area of it. So L is length, A is area. And generally, wires are circular, and so the area will end up being either pi r squared, or more often you're given the diameter of the wire, so it would be pi times the diameter squared divided by 4. And in the lab this week, I have a table of diameters for wires of different gauges, and it should pretty well cover all of the, in fact, I'm sure it covers all of the diameters of wire that you'll encounter in the lab, and so you'll deal with that. This is the reason that they make wires thicker and thicker. If you've got 14 gauge wire in your house, for instance, that's a particular diameter. 12 gauge wire is a quite thicker diameter, harder to bend those 12 gauge copper wires. If you're putting in an electrical outlet or something like that, I did it in a whole room in my house, and it was probably a little bit of overkill, but anyway, it was adequate. Also, I noticed one time I was putting an outlet in my garage in December, and it was really hard to bend the copper wire. The temperature was, maybe 15 degrees in the garage. I had the door open because I was going in and out of the garage while I was doing it. And it was really hard to bend the copper wire under those circumstances. And it was 12 gauge wire that I was using too. So there's a Wikipedia article. For the longest time, I didn't know why the wire gauge system worked the way it did. The smaller the number, the thicker the wire is. And I didn't happen to know how it was defined until I found this Wikipedia article on it that went into quite a bit of detail about it. And if you're curious about that, you could track down the article on wire gauges. But anyway, that's not all that the resistance depends on. It also depends on this quantity that we use the Greek letter rho for, and rho is the resistivity. So, and it's a property that if you're dealing with pure copper wire, every sample of pure copper is going to have the same resistivity. It does vary with things like temperature. It'll also vary tremendously if you start putting impurities into the wire. And so sometimes there may be reasons to do that. or if you're using alloys where you're using different mixtures of metal. And one of the things in the lab is that there's some wire that's of indeterminate metal. I have no idea what it is. It just says NS on it, and I don't know what that stands for. I looked it up one time and can't remember anymore what it was, but at any rate, the resistivity is the property that we're after in this lab. And so I'm going to bring that PowerPoint thing back here and have a look at it, which should still show up on your screen, I think. You see something that says Engineering Physics Lab Measuring Resistivity? Okay, good. Oh, I've got you guys turned down today. Okay, here's one of the things that we're going to be measuring the resistances of, and I've got this set of 4 different coils of copper wire. This nickel wire we're not going to mess around with, but if I connect here at number 1 between these 2 terminals, I'll measure the resistance of this coil here. I guess I could make that more easily visible if I use my laser pointer instead. Anyway, we'll connect between these 2 terminals to measure the resistance of that and so forth. And I think I forgot to measure the resistance of this 2000 centimeter coil of number 30 copper wire. I didn't do it with the good ohm meter that I have, or at least if I did, I didn't take a picture of it, and so I don't know what it happens to be. And I might be able to run out to school later today and just measure that one and try to get that into our data mix as well. But that's one of the things that we'll be measuring. And the other is these 5 coils of number 30 NS wire, whatever the heck that is. And so I did happen to take measurements of all 5 of these things, and we'll be able to get the resistivity of whatever it is that this wire is made out of from those measurements. And that's how it'll work. Now, for one set of measurements, I used an ohm meter that's very much like the one you have, that'll measure to a precision of 1/10 of an ohm. And this is the resistance that it's showing when I have the leads plugged into the thing, and I've got alligator clips on the end of them, and I've got the alligator clips chomped to each other, and I get a measurement of 0 ohms on it, or 0.0 ohms on it. And then I go ahead and measure the resistance of all these other things, and I show you pictures of all those measurements, so you can use these pictures for getting your data. And I've got a film that I'll put up on Wikipedia, or on Canvas, but I'll also put the PowerPoint itself up there, so you can just click through the slides if you want to, if you have PowerPoint. And this is just the last measurement. I could only get about 4 on a page in PowerPoint. So there's that one. And then I do the same thing with the other coils, the 4 coils that I've got there. And at least with this ohm meter, I also did it with the 2000 centimeters of the number 30 copper wire. And so got that one done. And then I bought one of these meters last year, and I can't remember how much it was. It wasn't cheap like your digital multimeters are that are less than $30. This was a few $100s, but these meters have the ability to measure to the nearest 1,000th of an ohm. And so when I connected the leads, just chomped them directly together on this thing, I did not get 0.0 ohms. Although if you rounded that to the nearest 1/10 of an ohm, it would be 0.0, but I got 0.031 ohms. And so much greater precision with this thing. And it's kind of fun to deal with. And so I took the measurements of the little copper coils, or no, little NS coils, whatever that is, with that one, and got more precise results. And I'm hoping that with these more precise results, and that's just the longest of the things again, I'm hoping with the more precise results that we'll be able to maybe zero in on whatever that wire happens to be made of, if we can find a table that has enough values on it out there somewhere. And so then I took the measurements of the 4 coils with the straight copper wire. And again, I forgot to take that 2,000 centimeter length of copper wire, but I may just go out and take a picture of that and add it to your things. So it was actually kind of neat. I've been hoping for something like this for years, and finally got one last year, assuming that we would be teaching live and that you'd be able to use this yourselves in person, but we won't do that. But for the lab, you'll be making a bunch of different measurements. And I wrote this lab mostly for some of my lower level classes where the people are pretty good at, or learning to make graphs, I should say. You're all pretty good at making graphs, but I'm still going to have you do the graphs the same way, except you get to do them in Excel. In those classes, they have to do them by hand. And I'm going to switch back here and go to the visualizer. Wow, it's a long ways away from me. Hopefully that's showing up again. In the first set of measurements where you're dealing just with those little coils of NS wire, they all happen to be the same gauge. And so they're all going to have the same cross-sectional area. But what I have you graph on for that is to make a graph of the resistance versus the length. And because the resistance has this relation, if I reorganize this stuff, it looks like that. Rho L over A is what it happens to be. But if you graph resistance versus length, so R in ohms on the vertical axis and length in probably centimeters would be convenient for this lab. On the horizontal axis, you'll get a bunch of data points that are probably pretty well linear, and you'll be doing this for 2 different sets of data, but that's okay. Anyway, the slope will equal the resistivity divided by the cross-sectional area. So the slope by itself is not the resistivity. But that's one of the pairs of graphs that you'll make. And this time you'll have 2 sets of data. I only mentioned one in the lab, but I'd like you to make separate graphs, although you might be able to get them on the same piece of paper. Make a graph of R versus L for the old, just the simple multimeter data, and then for the much better digital or the desktop multimeter, and get separate graphs. But they could go on the same page because the measurements are going to be roughly the same. Then for the second part, when you're measuring the copper coils, and again, I'll try to get that additional one for you, they're not all the same cross-sectional area. And so they're different gauges of wire, which means they'll have different cross-sectional areas. Now they do kind of match up in, there are 2 with one gauge and 2 with another gauge. And if I get that 5th one, then you'll have a 5th data point that has yet another gauge. I think it's 30 gauge wire, and the other 2 are 28 and 22, if I remember right. Let's see. Well, I can't see them right now, but anyway, for that graph, second graph, and second graphs, actually, I want you to make a graph of R versus L over A. Okay, so it's the length divided by the cross-sectional area, and so this will be something that you'll have to calculate for those different things, but it's a fairly simple calculation. One of the hardest things people have with this lab is calculating the cross-sectional area, which is going to be pi times the diameter squared over 4. And diameters are what are tabulated for wire gauges, not the radii. So just do it that way. But the diameters are usually in millimeters, and I see lots of mistakes for converting from millimeters squared to meters squared or centimeters squared. And so make sure you do that correctly. It's not just a factor of 10 to the third or whatever you might be thinking. So check your units as you're doing the unit conversion and absolutely convince yourself that those are going to be correct. Because I've had a lot of people off by a factor of 1,000 when they calculate those areas. So watch out with that. But anyway, if you graph R on the vertical axis in ohms, and L over A is going to end up having units of maybe meters to the -1, this would be L over A, or because it'll be meters on top and meters squared on the bottom, so meters to the -1. But the slope of that graph is just going to be the resistivity, and it'll have units of this divided by that, which could be ohm meters or ohm centimeters, and it's your choice. Sometimes you'll see the resistivity out on the internet or in whatever table you find in ohm meters, and sometimes you'll see it in ohm centimeters. Oftentimes it'll be in, well, they'll just ignore the factor of times 10 to the minus whatever it is that shows up in there, and that'll be at the top of the table, and so you need to watch out for that. It'll say something like all values times 10 to the minus whatever, or something like that. So read the tables carefully when you're looking at that. For this lab, it's mainly gathering the data, which I've already done for you, except for that one measurement. And let's see, gathering the data, making some graphs, and then answering some, doing some simple calculations as you go through it. But then at the tail end, I have you write a 200-word sort of mini little essay thing explaining the difference between resistance and resistivity and some other things in there. So it's not going to take anywhere near as long as a full-blown lab report. And I'll have it due next week after the test sometime, probably next Wednesday or Thursday. So, but you could start monkeying around with that fairly soon. This is something that, man, when I went through physics courses, I never learned anything about this, but I find it kind of interesting, and it's nice to have a little bit of a background in some of this stuff. I had friends in graduate school who studied resistivity of materials, and that branch of physics is called condensed matter physics. They do a lot more than just that, but I'll tell you a story about one of them. He was studying, or everybody in the lab he was working in was looking at this one sample of material that seemed to behave oddly. And something that happens with resistivities is that they vary with temperature, and usually, almost always, they'll decrease with temperature. And so as the temperature gets colder and colder, their resistivities will decrease. This would be temperature in Kelvin, and resistivity in something like ohm meters or whatever it happens to be. And in the lab they were working in, they were actually dealing with temperatures of millikelvin. And so they were under 1 Kelvin of temperature. and they had this experimental setup they'd made, and they would put it in I'm not sure, a cryostat or something, where they would cool it down ever so gradually, and they would do a kind of vacuum pumping to diminish the temperature even further. So way down there in low temperatures, like this might have been 10 millikelvin and this might have been 15 and stuff like that. And they were interested in seeing if they'd come up with something that became a superconductor. And that was big in the news when I was in graduate school. They found the first high temperature superconductor. And in this case, high temperature meant warmer than the temperature of liquid nitrogen. And liquid nitrogen is really cold, but everything that they dealt with before in terms of superconductors, they had to get down to a temperature of well under the temperature of liquid nitrogen, and liquid helium might have been something more practical for it or something like that. And liquid helium is a whole lot more expensive than liquid nitrogen. Liquid nitrogen is practically free. You can buy it in Moses Lake. I bought some 2 springs ago when the chemistry students were making ice cream with liquid nitrogen. And so that was kind of fun. But anyway, they're studying this stuff, and they'd be cooling it down, which took a long time, like hours. And they noticed that at some point in the cooling process, all of a sudden there would be kind of a jump that the resistivity made, and then it would go back to its kind of linear decrease again. And I've probably got the slope too steep on this, I'm not sure. But this jump would kind of move around on it, but it was always kind of in the same region of the thing. And this was something that they would often start the experiment the night before or the day before or something like that, and they would let it run, and they had computers that were keeping track of the data and stuff like that. But this was very mysterious, and as far as they knew, they hadn't seen it before. And it was driving them nuts. They thought, okay, we've got an impurity in the sample. And so they took the whole getup out of the refrigerator, basically, that they had it in, and they would bake the sample in an oven to boil off any impurities that were on it, and set up the experiment again and go through it. And it would take like a week between cycling of the thing. And so they'd do it again, and they'd get this same bump again, but it might move around on the temperature. And so it would occur at different places. And they figured it, okay, it's probably not gonna get us a Nobel Prize, but this is an interesting phenomenon. So maybe we can write this up or something like that for physical review at least. So, but still, their advisor suspected that it was just a problem with their experimental setup. And he was going on vacation to his lake cabin in northern Minnesota. This was the summer of 1988. And he told the 2 students that were working for him in this lab, all right, I want you guys to solve this problem by the time I get back. And when you solve it, give me a call at the cabin, but don't call me for just more reports of problems. And so he was sort of mad about the whole thing, and he figured they'd screwed up somewhere. So this particular summer, the guy that I knew in the lab was somebody that I played, all through grad school. I'd played softball with him, actually shared an office with him my first 2 years there. But we played softball in the summer and spring, and hockey in the winter. And then after softball all the time, we'd go out for hamburgers most of the time. And the summer of 1988 in Minnesota was the hottest summer on record for a long time. And there were like 45 days above 90 degrees there. And it's pretty humid back there. So when you get a day that's above 90 degrees, it probably won't cool down below about 77 at night, because the air's so humid, it holds a lot more. And so it was miserable. We lived in a townhouse apartment at the time, and the temperature in our apartment would be down to 88 by morning. And we didn't have air conditioning. So it was kind of a hot, sticky summer. However, this one night we go out for softball, or played softball, and then went out for hamburgers afterwards. And I was sitting across the table from him, and he was kind of glum that night, and said, "What's the matter, Pete?" And he said, "Well, you know that experiment we've been having trouble with? I figured out what's wrong." And this morning I went into the lab early, and I got there about 6 o'clock, and I was keeping an eye on things, and I wanted to see what was going on when that spike occurred. And so I was watching the resistance measurements on this thing, and I saw the jump. And at the same time, I heard the air conditioning for the building turn on. And the little bit of spike that had happened, or something that had shown up in the electrical circuits of the building when the air conditioning came on, had caused that little blip in their measurements. They thought they'd had everything completely isolated from the electrical system of the building, but apparently not. And instead of being able to write this up for the physical review, it might make a mention in something like Air Conditioning Monthly, but probably nowhere else. And my friend said, "Yeah, the other guy and I tossed coins to decide who was going to get to call Wyman." That was their advisor, and I lost. So he had to call the advisor the next day and tell him just what the problem that they'd been studying for weeks happened to have been. So that's something that can happen. There was no change in the resistivity that behaved like that. If they'd done it at a different time of day, it would have been a nice regular straight line curve like that, which was kind of what they were studying anyway, but this was all garbage, turned out. All right, well, that's enough about resistivity, and you'll get some experience dealing with that. Today, we're going to talk about something that can be done with capacitors. And, I guess I'll still be writing on paper here for this, so we'll go ahead and do that. But this has to do with, I had stuff up there on the cylindrical capacitor, which we may need for one of these. But that model of the capacitor that we made, the parallel plate capacitor, we were assuming just that we had something like air in there. However, it is possible to put other material in there, and we would refer to that material as a dielectric. And so that can increase the capacitance, and it does it in kind of an interesting way. What the dielectric does is, for a particular amount of charge on the capacitor, we'll suppose we have a Q up here and a minus Q down here. So you can keep the same amount of charge on the capacitor, but the dielectric that's in there, this will be a positive charge up here and a negative charge down here. The dielectric is a material that can polarize in a way, and so up here near the positive charge on the top plate, you'll get on the top surface of the dielectric some minus charge, and they're usually just atoms that orient themselves, or molecules that orient themselves in such a way that you'll effectively have some minus charge up here that will kind of partially cancel the electric field produced by these positive charges. And then on the negative plate down here, you'll get atoms that orient themselves in such a way that they'll have a positive end down here, and they'll partially cancel the minus charge down there. Now, you keep the same amount of charge on the actual metal plates of the capacitor, but you diminish the potential difference in here because the electric field will be less. And the effective charge distance or distribution that determines the electric field strength in here will be less. And so remember, the electric field strength is the charge density divided by epsilon naught. Well, the charge density, there's the regular charge density, but it'll be partially canceled by an induced charge density. And so you end up with a smaller electric field, and that smaller electric field means there's a smaller potential difference here, but the capacitance depends on the amount of charge you can put on there for a potential difference, but the potential difference gets less, which means the capacitance actually increases. And the number that's usually used for the capacitance, or the amount that it diminishes by, is called the dielectric constant. So and the dielectric constant used to be, they made a big deal out of using a Greek letter kappa, but it seems like now everywhere you look you see a K in Times New Roman font instead. And so I don't know if they've call it kappa anymore or not, but this is a table that's out of your book of values of the dielectric constant at 20 degrees Celsius. And a vacuum has a dielectric constant of 1 exactly. Air has a dielectric constant of pretty close to 1.00059. And it's kind of similar to the way air's index of refraction compares to that of the vacuum. The vacuum index of refraction is exactly 1. Air is like 0.00029 or something, if I remember correctly. But however, if you increase the density of the air, 100 atmospheres is kind of crazy dense, but it goes up to 1.0548. I don't know why you would care about that, because it's not going to be a practical way to maintain a capacitor. Things like Teflon, 2.1. Nice thing about Teflon, I don't know if you've ever monkeyed around with the Teflon tape that you can put on things like pipe threads for plumbing, but you can stretch that stuff really thin. And so it's got a pretty good dielectric constant, and it can be stretched thin. So if you think of oh, by the way, the new formula for the capacitance is going to end up being kappa epsilon naught A divided by D. So you just multiply the regular capacitance by kappa, and you can get an increase in that. And it has a bunch of different ones here. Polyvinyl chloride, plexiglass, glass. Used to be, they would actually use sheets of mica in capacitors. Mica is a mineral that shows up in rocks. If you ever look at a granite rock, which is an intrusive igneous rock, it's molten rock that condenses from a liquid state to a solid state very slowly underground, and it'll form crystals of various types in it. And if you see mica, it's kind of a shiny looking thing in there, and it has the property that it forms a crystal with very thin sheets, and you can slice those sheets out and use it for a dielectric in a capacitor. And so that was something that used to be used. It's not so easy to work with, but they did anyway. Teflon's a whole lot easier to work with than some of these plastics are too. So you can have stuff like that. You can even use water as a dielectric. Pure water doesn't conduct electricity. And so, and it's also a polar molecule. That's what makes it good at dissolving things. So you could use that, although you'd probably have to be careful about your orientation of your capacitor if you've got water in there. So I guess you'd have to worry about that. But let's look at some capacitor problems. This first one, actually it has nothing to do with dielectrics. So let's imagine we're going to make a parallel plate capacitor, and we have available 2 sheets of copper, a sheet of mica. The 2 sheets of copper will be the upper and lower plate of the capacitor. But then between them, you could either put a sheet of mica that has a thickness of that and a dielectric constant of that, or a sheet of glass, which is a whole lot thicker, but has a larger dielectric constant, and then a slab of paraffin, which I don't think was on our table, but it's got a value of that. To obtain the largest capacitance, which sheet should you place between the copper plates? Well, the capacitance here is going to be kappa epsilon naught A divided by D. And what we're varying by using these different materials is the ratio kappa over D. And so epsilon naught doesn't change. That's 8.85 times 10 to the minus 12, and the area of the copper plates is not going to change. So it's just kappa and D that do. So for the mica, you would have a thickness of 0.10 meters. So kappa over D is going to be 5.4, that's a D, divided by, I guess we could call that 1.0 times 10 to the minus 4th meters. So this thing would end up being 5.4 times 10 to the 4th meters to the minus 1, that ratio would. For the glass, we've got a 2 millimeter thickness and a dielectric constant of 7.0. So 7.0 divided by 2.0 times 10 to the minus 3rd meters. And you can do that in your head. 7 divided by 2 is 3.5 times 10 to the 3rd meters to the minus 1. So this is more than 10 times smaller than the mica was, so not particularly impressive here. And then the paraffin, which is kappa is 2.0 and then 1.0 times 10 to the minus 2. And we could have done these in our heads actually, but this will be 2.0 times 0.0 times 10 squared meters to the minus 1. So this one, the paraffin, is a factor of 10, more than 10. It's actually more like 17 and a half times smaller than the glass. And the glass is more than, well, I don't know, about another 17 times smaller than the mica. So the mica by far would be the better choice if you're trying to make a capacitor out of that. Although this isn't the only thing to consider. Something else that you might want to think about is the dielectric strength. And I can't remember if they have that in your book anywhere or not. I didn't see it in this section. Yeah, I'm not sure. Let me see where I can find that, if they've even got it in this book. Does anyone remember seeing it in an earlier chapter?
I think talked about it right at the end of 24.4.
Okay, but did they have a table of values or not? Dielectric breakdown, 804 and 805. Oh, it should be here. Oh, it is in there. Okay, it's in 24.3. They've only got it for a few, I guess. But, and they don't have air. Well, maybe they mentioned that. Yeah, the dielectric strength of dry air is 3 million volts per meter. And for these other things, this is like 30 million volts for polycarbonate, 60 million for polyester, 70 million for polypropylene. Polystyrene is 20 million, and Pyrex glass is about 10 million. So, yeah, somewhere I've seen it for things like, well, it might have been in a different book that I used to teach out of, but they had, when they had the values of the dielectric constant, they also had the dielectric strength next to each one of them, which was kind of interesting to see. And so you realize that, yeah, you can make Teflon super thin, but then you have a capacitor where you can only charge it up to a particular potential difference, because otherwise you break the dielectric down. But that's something that also would have to be taken into account with the design of this thing. And they mentioned in here, in this section, yeah, there's a kind of electrolytic double layer capacitor. They put tiny carbon granules adhered to each plate, and those have the effect of vastly increasing the surface area of the plates themselves, and so you can end up with a lot more charge on them. And they say you can have a capacitor of this kind with a capacitance of 5,000 farads that'll still fit in the palm of your hand. And 5,000 farads is crazy big. I thought those ones that I had that were a few hundred farads were kind of impressive, but that would be pretty amazing. So those are things that you can do with dielectrics, is increase the capacitance. And really, if you think about a parallel plate capacitor, if that's all you had to it, really, what can you do with that? If you're trying to maintain an air gap, that's going to be really hard. But if you stick a dielectric between them and you have pieces of metal foil instead, then you can have the picture like on, I think there was a picture of this somewhere, maybe not. Maybe they didn't. I thought I remember. Oh, here it is. On this page, you have your metal foil, and in between you have the dielectric, which could be plastic sheets, and you can roll the whole thing up and have a much more compact thing, even though you still have the same effective area. And this, the mathematics of this will still be pretty much like a parallel plate capacitor, but even though it looks like a cylinder when you roll it up, but it's not quite acting like a cylinder. So that's how they make those little tiny capacitors. And the ones that are in your electronics kit, I'm going to dig those out real quick. Let it sit in here. These are the capacitors that are in your electronics parts kits. And these aren't big capacitors. Their real function isn't to store energy so much, but they have other properties that show up in a circuit. And somewhere on these things, actually, I don't even know. I can't read what that is. I would need a good magnifying glass to have a clue what these things say on them, but there's probably some information about their capacitance on there. This one has even smaller writing. Actually, I think it says 22 maybe. Now, if it's that small, most likely that's 22 picofarads. That I can't even recognize as a number. It looks like the ink got smudged. And I don't know if we've got much variation in these things or not. Yeah, can't read those. These are small capacitors though, and but they'll still serve a purpose. One thing they do is if you've got an alternating current circuit, and they'll have a particular properties in there that become advantageous there. But if you've got an alternating current circuit and you accidentally get some direct current in there, the capacitor will kill that direct current because you can't have current flow across these parallel plates. And so that's one function that they can serve, is to, the alternating current can still do its alternating current thing. Alternating current goes one way for a while and then the other way for a while, and it'll be doing that on both sides of the capacitor, which basically means you're building up charge on the capacitor and taking it off again. And still, for alternating current, they can behave kind of nicely, but direct current will not get through the thing, and so it'll completely block that. You can also design circuits that will eliminate particular frequencies, and for that you need a resistor and a capacitor, and you can put those. I can remember the first car stereo I ever bought, I kept picking up this really loud low frequency sound in the car stereo. Then I read a little bit about it and found out how to make a circuit that would kill that. So I went to, in those days it was Radio Shack, where you got electronics parts, and got a capacitor and a resistor and made it, and it cut that stuff out. Kind of a weird thing to be doing with this high-tech device. So I don't know where I put the rest of the problems I was going to solve. I don't know if I even gave you a homework question on these things, but it's kind of a minor topic, but it's something that may show up if you keep going in this stuff. Parallel plate capacitor has a capacitance of 50 picofarads, which would be, and I'm going to call this C naught. That would be the capacitance. Well, we'll just call it C. What the heck? 50 times 10 to the minus 12th farads. That's what the P stands for. So if its plates each have an area of 0.35 meters squared, okay, now the capacitor is not going to be that big. This is going to be rolled up somehow, or some tiny little sandwich. But the area is 0.35 meters squared. What's their separation? If it's air, so, well, maybe we do imagine this thing as having an air gap between here. And I didn't draw it very well, but they'll have a separation of D. So C is epsilon naught A divided by D, and we're supposed to find the separation. So a little bit more work will give us D is equal to epsilon naught A divided by C. So, oh, I just saw something about epsilon naught. Let's see. A different way of expressing it. 8.85 times 10 to the minus 12th Coulomb squared per Newton meter squared. And I think what they did was, let's see, if you imagine that combination of units, you leave a Coulomb on top and a Newton meter on the bottom and another meter on the bottom and a Coulomb on the bottom. And if you fixed these units, you would actually turn it back into this. But this Newton meter per coulomb down here, a Newton meter is a joule. That's a joule per coulomb. That's a volt. And so you can think of the units for that thing as being coulombs per volt meter. But the coulombs per volt, that's a farad. And so you can think of the units of epsilon naught as being farads per meter. So epsilon naught, you can think of it as 8.85 times 10 to the minus 12th farads per meter. All right, so that's what we'll use on here. And the distance between these things is going to be 8.85 times 10 to the minus 12th farads per meter times the area, wherever it went, 0.35 meters squared. And then I'm dividing by the capacitance, which is, let's see, 50 times 10 to the minus 12th, just plain farads. So the farads will divide out, and what I end up with is meters. So that's kind of nice. And then since I've got a 10 to the minus 12th top and bottom, I'm just going to ignore those things. And whoops, I was going to ignore them. So and I get a separation here of, I think, let's see, 6.2 times 10 to the minus 5, or maybe just 6. I've only got a 50 there. So 6 times 10 to the minus 2 meters. That's a lot. That's 6 centimeters. So this is, no wonder it doesn't have a very big capacitance. If we fill the region between the plates with material having a dielectric constant of 5.6, what's the capacitance? Well, it's just going to be 5.6 times that. So for part B on here, if that is a part B, the new capacitance is just going to be 5.6 times 50 picofarads. So that's all you have to do to figure out the new capacitance there, is that. Okay, I don't think I even gave you any homework on this that I remember. I might have, but I don't think so. So that'll be it. Tomorrow, I'll provide you, we'll have a review sheet for the test, and I'll give you an old test so you can see what kind of things. Test will be Monday. We need to zero in on some kind of a 2-hour block when people could take the test. Let's see, I may have your test maybe overlap with the one for my physics 114 class. So I'll have people taking different tests at the same time. They're only going to get 75 minutes for their test. And yeah, so you might be interrupted a little bit, although if you have the sound turned down or aren't listening to me, it might not distract you, but I would cut their test off after 75 minutes and you guys could keep going for 2 hours or for a total of 2 hours. So, but we'll be doing that tomorrow. And stop sharing there. So if there aren't any questions, and I think I will run out to school this afternoon and measure those, take those resistance measurements with the better meter that I forgot to do. And I'll add those pictures to the PowerPoint show before I post it this afternoon. So we'll have that. So, any questions? Okay, I'll see you tomorrow.